All right, what's up, everybody? It's Professor B, and I'm back today with another problem. We're going to be doing some Thevenin today, so let's just jump straight into it. The question is asking us to draw the Thevenin and the Norton equivalent circuit. So in order to do that, we have to find our V Thevenin, which is going to be the voltage at the terminal A, and then we also have to find our I short circuit, which is also equal to our the Norton current, and then the C Thevenin, which is our impedance, which is also equal to the Norton impedance. So let's just jump straight into it. And first things first, we're going to begin labeling our currents, right? So we can just call this I1. We're going to call this I2. And now I'm going to label my nodes. Let's call this node Vx. And then after the resistor, let's call this node V. And then after here, we're going to call this node VA, which is the same node as this one right here. Okay, so then doing KCL at Vx, we're going to have the convention that we're going to use is all the currents that enter equal the currents that are leaving. So therefore, we can say that I1 is equal to I sub x plus I sub 2. Now, using our nodal analysis, I1 is going to equal 15 minus Vx over 3000, and then I sub x is just going to be Vx minus 0 because it goes to ground, right? This is connected to ground. Over minus 6000 J, right? And then plus I sub 2, which you may think that it's Vx minus V, but it's not because it's an open circuit. There's no current, so therefore the current I sub 2 is just equal to 0. So now multiplying, we can like cross multiply, and we're going to have minus 6000 J, 15 minus Vx equals 3, or we just say that is equal to Vx, and then all this over 3000, right? So you put in your calculator, we have minus 2J, 15 minus Vx is equal to Vx. So then you have minus 30J plus 2J Vx is equal to Vx. So then you have minus 30J is equal to V1 minus 2J. So putting that in your calculator, you should get, we have minus 30J, right? Okay, so minus 30J all over 1 minus 2J, and you should get 12 minus 6J. Well, that's going to be our voltage at V sub x, right? So now let's find our voltage at V. So our voltage at V, we could say that it's, we could say that our voltage at V is going to equal to Vx is equal to V plus I2 times that 4 kilo ohm resistor, right? So now we know that open circuit has no current, especially on this side of the circuit. So therefore my Vx is going to equal V, and this goes to 0. So then if my Vx is equal to V, then that means that V is also 12 minus 6J. Now that we found Vx and V, we can find our voltage at VA by applying the same logic. So we can say that V is equal to VA plus 2000 times I sub x. Right, so we know that V minus 2000 I sub x is going to equal to VA. And we already know what our I sub x is, right? I sub x is, we see Vx all over minus 6 J kilo ohms, right? And then multiplying by J, we're just going to have J Vx all over 6,000, I believe. So then we know that V is equal to 12 minus 6J minus 2,000, and then our I sub x is going to be J Vx over 6,000, just equal to VA. And then we have 12 minus 6J. This is, I believe, 2,000 over 6,000 would be 1/3 J Vx is equal to VA. And then we have 12 minus 6J minus 1/3 J. And then we know that Vx is equal to 12 minus 6J, right? Because we just found Vx, right? We had found Vx by doing KCL. And then once we found our Vx, we tried to find V by using our Ohm's law elementary equation. But since there's no current, it just shows you that Vx is equal to V. So therefore, this is equal to VA. And then continuing, we should have 12 divided by 3 is 4, and then you have plus 6 divided by 3 is 2J squared, which is equal to VA. So then you have 12. J squared, remember, is -1, so 2 times -1 is -2. So then you have 12 minus 2 minus 6 minus 4 is -10 is equal to VA. So then you have 10 minus 10J is equal to, and that is our Thevenin voltage, right? This is our Thevenin voltage. I should probably name it like this. Let me see. Equals V Thevenin, right? And then this is our Thevenin voltage, correct? So now we have to find our I sub C. So when we do I sub C, we're gonna have the same circuit. Let me just copy and paste the circuit so I don't have to redraw it. Oh boy. And that should do it. That should do it. And then we copy. And now we're gonna come back here and paste it. Oh boy, that's not working out. All right, we're just gonna have to redraw the circuit then. I'm gonna have to redraw the circuit. Okay, no worries. We can redraw the circuit. Okay, so again, we have this 3 kilo ohm resistor, and then we have plus minus, right? 15. And then here we have that capacitance, which is -6J kilo ohms. And then here we have a resistor. And here we have our dependent voltage source. And then we have our A, and then we have our B, right? So this is positive minus 2,000 I sub x. What was this, 4 kilo ohms? And then don't forget that we have our, we have our I sub x right here. We named this current right here I sub 1. And we named this current right here I sub 2, right? Name that current I sub 2, right? Okay, so now we had labeled our nodes. We had labeled this node to be Vx, right? So we can just call it Vx1, and then this one is going to be V1, and then this one is going to be VA1, right? So the moment that we short our terminals, we short it. Let me see. We short out our terminals, and this VA is now 0 because an ideal wire carries no voltage and no resistance. It's only just current. So we know that v sub a is equal to 0. Right? And we had determined that v sub x, to be 12 minus 6j, but that's not going to be the same case because this right here is a different circuit than when we're finding our I short circuit. So we apply the same thing and we do our KCL at Vx1, and using the same convention, entering current equal leaving current, I1 is equal to Ix plus I2. So then again, I1 is just going to be 15 minus Vx1 all over 3,000. And then we know that I sub x is just equal to Vx1 all over Vx1 minus 0 over negative 6,000j. And then remember how earlier we had open circuit and our I sub 2, right, this guy right here was 0 because there's no current. But we short circuited, so now we do have current. So then I sub 2 is just going to be Vx1 minus V1. And that's all over 4,000. It's all over 4,000, right? Okay. Now, I think we can multiply everything by 72,000. So if we multiply everything by, I'll put right here, 72,000. So 1, 2, 3 divided by, this is going to be 24 minus Vx1 is equal to 72,000 divided by 6,000 is 6 over 5. Sorry, that's 12. And that's going to be JVX1, and then 72,000 divided by 4,000, that's plus 18 VX1 minus V1, right? VX1 minus V1, right? Okay, so then from here, we can say that from here, we can say that 24 times 15 is 360 minus 24 VX1 is equal to 12J VX1 plus 18 VX1 minus 18 V1. Right, so then we need to figure out what my V1 is in order to find what Vx is. So using our using Ohm's law, we can say that V1 is equal to 2000 Ix plus VA. But remember that VA is 0. The moment that was shorted, there's no voltage there. So V1 is just equal to 2K times I sub X. So now, doing our equation, we have 360 minus 24 Vx1 is equal to 12J Vx1 plus 18 Vx1 minus 18, and then V1 is going to be 2000, and then I sub x, we know that I sub x is, let me see, what would I sub x be? It would be Vx1j all over 6,000. That's what that would be. And then we continue. We have 360 minus 24 Vx1 minus 18 Vx1 is equal to 12J Vx1 minus, well, what we would have here, we would just have 18 times 2000 times Vx1j all over 6,000. Right, so that should give me 6, and then we'd have 360. Let me see, minus 24 minus 18, I think that's minus 42 Vx1, and that's equal to 12J Vx1 minus 6 Vx1J. And that is exactly what I have right here. Sir, and then we have 360 minus 42 Vx1 is equal to 12 minus 6 is 6, so then you have 6J Vx1. 360 is equal to Vx1, you have 6J plus 42, so we can say that Vx1 is equal to 360 all over 6J plus 42. I get 8.4 minus 1.2J. Let me double check that that is correct, and it is. So now we have our voltage. Remember that it is not the same voltage as this Vx because this is a different circuit than when we connected the terminals A and B. So now our new voltage with this new circuit is 8.4 minus 1.2J. Now that we have that, we need to find the voltage at V1. So we can say the voltage at V1 is going to be Vx is equal to V1 plus I2 times 4,000. So then you have Vx1 minus V1 all over 4,000 is equal to I2. Is equal to I2. And we know that Vx1 is 8.4 minus 1.2J. And V1 is what we're looking to find. Divided by 4,000 is just equal to I2, right? And then 8.4 minus 1.2, I'm sorry, we're not finding V1, we know what V1 is. V1 is just minus 2,000 I sub x all over 4,000 is equal to I2. So then our ISC is going to be equal to that current going through the 4 kilo ohm resistance, right? So then doing our simplification, we know that 2,000, and then we know that I sub x is equal to, let me see, what is I sub x? I sub x is just Vx1 over, right? I sub x is just Vx1 over minus 6,000 J is equal to I2. This is going to be our circuit current, short-circuited. So then we have 2,000 divided by 6,000 is going to be, let me see, it's going to be 1/3, I believe, right? So it's going to be plus 1/3 J Vx1 equals I2, 8.4 minus 1.2J plus 1/3 J, where Vx1 we had found to be 8.4 minus 1.2J is equal to I2. So then distributing, we have 8.4 minus 1.2J plus we have 8.4 divided by 3, that should be 2.8. Is it a minus? I don't see that we have a minus 1/3. Let me see. So we have what, Vx1 all over minus 6,000 J times J all over J. Then you should have Vx1J all over 6,000, right? So that should be a positive. That should be a positive right here. This turns into a freaking positive. And so with this minus 2.8J, and then you have plus 1.2 divided by 3 is going to be 2 over 5, which is plus 0.4, but you also have J squared. I is equal to I2, so then you have 8.4. What's 1.2 minus 2.8? I believe that is 4. Minus 4, I believe, right? So let me double check. Minus 1.2 minus 2.8. That's minus 4, right? That's minus 4j. And remember, we have, okay, we got rid of this. And remember, we have our j squared, because we know that our j squared is equal to -1, because j is equal to the root of -1. So square both sides, you just are equal to -1. So if that's -1, then you're going to have -0.4 plus 8.4. It should give you 8 minus 4j is equal to I2. And remember that we have our 4,000. Can't forget our 4,000, right? We should 1 over 4k, 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 and then this is 1 over 4,000. So then our current I sub 2, it's equal to our short-circuited current. And if you put that into your calculator using complex numbers, you're going to have 8 minus 4i all over, or 4j all over 4,000. You should have about, let me see, you should have 2 times 10 to the -3 minus 1 times 10 to the -3j. So our current short-circuited is going to be equal to 2 minus j in milliamps, right? That's going to be our current in milliamps. So now that we have our Thevenin, and we found our short current, now we can find our Thevenin, which is equal to VOC over ISC. And then VOC, we said that the Thevenin was 10 minus 10j. Right, we said that it was 10 minus 10j. And then ISC we just found to be, let me see, what is it? So it's milli, right? So we know that 1 milliamp is equal to 10 to the -3 amps. So this is in milliamps times, we know that 10 to the -3 amps over 1 milliamp. So we have to turn this as 1, 2, 3. So 0.02 amps. So 0.02 minus 0.01 j, that's going to be in amps. And putting that into your calculator, you should have 10 minus 10j over 0.002 minus 0.001, that's j. You should get 6,000 minus 2,000 I amps. And if you want it in milliamps, it's just going to be 6 minus 2j milliamps, right? Well, we know that our VOC is 10 minus 10j, and our short-circuited current is 2 minus j milliamps. So remember that the question wants us to write, or to draw, the equivalent Thevenin and Norton circuit. So drawing our Thevenin, we're going to have our voltage source, which is going to be VOC, which is equal to 10 minus 10j. Actually not a resistor, because we have an impedance. It's going to be impedance of Thevenin. And we know that our impedance is 6 minus 2 milliamps. And then our Norton equivalent circuit is going to be the current source, which is ISC, to be 2 minus j milliamps. And then this is also our Thevenin. And our Thevenin, we know that it's 6 minus 2j milliamps. And that is our equivalent Thevenin and Norton circuits. Thank you guys for watching.